So again, looking at the inverse cotangent, remember everything has to shift because the cotangent is the reciprocal of the tangent. So what we have are our standard functions where we just drew multiples from negative pi to pi. So currently, vertical tangent line test, pass. Okay, so we have a function here. The problem is if we draw a horizontal tangent line, I would pass through multiple because yet there'd be another one here and another one here and so on. There's infinitely many because we have these vertical asymptotes. So again, we need to limit our domain restriction, okay? So what we did was we limited from 0 to pi. So basically we just shifted, okay, making our function now 1 to 1. So when we limit our domain, this is y is equal to the cotangent of x, where we limit the domain from 0 to pi. And remember, these are not brackets because we have vertical asymptotes. Okay, so the cotangent of x, the domain, is all real numbers not equal to k times pi, meaning 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, okay, because they're all vertical asymptotes. My current range is all real numbers, or basically negative infinity to positive infinity. This is for my cotangent of x, standard function, okay? So what we did was we just said that we're going to limit the domain from 0 to pi, okay? We'll get positive and negative values that we need. And what we're going to look at now is switching the x and the y. So here we have y is equal to the inverse tangent of x, or the same thing would be the cotangent of x. I said tangent. So this basically looks like the tangent, except it's flipped, remember, because they're reciprocals. And if you recall, the inverse tangent was down from negative pi over 2 to pi over 2. So now this is going from 0 to pi. So we're going from 0 to pi. Okay, and we have our key values. Again, negative 1 and positive 1, but they're just key values on the graph. And this is sometimes challenging to sketch. Okay, just like that. Okay, so now our domain is our range from our original, which is all real numbers, or negative infinity to positive infinity. And then our range is from our restricted domain of the original, which is 0 to pi. Okay, and this is for the inverse cotangent. So when we deal with the composite function, again, what you're looking at is the domain for the inside. So I'm looking at the domain for the inside function. So my inside function here is the inverse. I'm focusing on the domain and what's going to make this work. So this is the cotangent of the inverse cotangent of x, which would be the same thing as the cotangent of the arc cotangent of x. It's just written it two different ways. Should be equal to x, provided x is any value. Because remember, the domain for my inverse cotangent is all real numbers. Okay, so what we're looking at here is the domain for the inside function. I'll write it right here. Okay. That should be a quote, not a parenthesis. So what we're looking at here is the domain for the inside function, which is f of x. So when I look at the domain for the inside function, okay, we're going basically, our restricted domain for the original restricted domain is from 0 to pi. So if I have any other value from 0 to pi on the inside, I need to make adjustments. So here we have the inverse cotangent of the cotangent of x, which would be the same thing as the arc cotangent of the cotangent of x, would be equal to x, provided my x value falls between 0 and pi, but not equal to pi. And again, we're looking at the domain for the inside function, which is why I'm highlighting it in green, because if you go up here, this is in green, just so you can see the correlation. Okay, so y is equal to the inverse cotangent of x, which is the arc cotangent of x. And basically what that means is x is equal to the cotangent of y, so these are solved for y, where Your x value goes from anywhere from negative infinity to positive infinity, and your y value is from 0 to pi, not included because these are asymptotes. These are not included because, well, I mean, negative infinity and positive infinity are not numbers. They're concepts.